Hi there. So today I'm going to talk about section 5.1, which talks about logs and their properties. Okay, so one of our motivating factors for talking about logarithms is the following. Suppose we wanted to solve something like 12 to the power of x is equal to 1,347. Okay? We could certainly estimate using trial and error just by plugging in different values for x to at least approximate what x is going to be, but we have no way to solve exactly for x. And this is something that we're going to see soon enough in these upcoming sections that we're going to want to be able to do. Okay? So our goal is to be able to take an exponential function like this and be able to solve it. Okay? So that's sort of our motivating factor. Okay? So since our motivation involves exponentials, let's go back to exponentials. Okay? Let's just take a very basic exponential function, say y equals a to the power of x. Now, one of the things that we saw for our general exponential functions is that our graph looks like this. Okay, we have a horizontal asymptote right here because remember, as x gets very small, our function values approach 0. Okay? One of the things that I'm going to mention about this function is that it's a one-to-one function. Okay? Recall, you have a function if it passes your vertical line test. In other words, each x value goes to exactly one y value. The other thing that we've talked about is one-to-one functions. We have that horizontal line test for one-to-one functions. Okay? Now, first off, what does that mean practically speaking? Well, again, in order to be a function, each x value has to go to exactly one y value. But in order to be one-to-one, each y value, in other words, each value in your range, can only be gotten to by one value in your domain. So in other words, everybody has a partner and only one partner. Okay? Now, what was the issue with a one-to-one function? Well, remember, functions need to be one-to-one in order to be able to have an inverse. Okay? We saw that if a function wasn't one-to-one, we could theoretically define an inverse, but it was not necessarily a function. Okay? So, in order for a function to have an inverse function, he needs to be one-to-one. This exponential function is one-to-one, therefore, we want to find its inverse. Okay? Well, how to find the inverse? Well, recall, you start out with your function, and then our first step is to switch our x and y values. In other words, x is equal to a to the power of y. Okay? Our next step then is now solve for y. Okay? Well, how do we get y equals here? Now, some people say, well, raise both sides to the 1 over y power, or take the yth root. Yeah, that would remove it from our right side, but that would just create a mess on our left side. In fact, it turns out that there is no way to do such. Okay? So we run into a problem here. We know an inverse exists, but we have no way to write it as y equals. Therefore, what we do is we say the following, okay? We know the inverse is equivalent to this statement. So what we do is we say x equals a to the y is equivalent to y equals log base A of x. Okay, this equivalence, as we saw in that previous section, is of crucial importance. All right, so again, I know it seems really funky that we suddenly came up with y equals log base A of x, but again, remember, we know an inverse exists, and we know that it's equivalent to this form here, okay? So I understand that logs seem sort of like out from left field, but I assure you that while we have this definition here, using this equivalence, everything is going to follow. Now, as I mentioned before, there are two bases that come up very frequently. Base 10 and base E. They come up so frequently that instead of writing log base 10, we just write log. And instead of writing log base E, that's actually called our natural log. We write natural, ln for natural log. So, couple quick things to show you is as follows. When you see y equals log of x, using this equivalence, that's equivalent to 10 to the y equals x. Remember, if there's no number written there, by default it's 10. 10 to the power of y equals x. In a similar manner, if you see y equals log x, the natural log of x, that's equivalent, remember that's a base of e to the y equals x. Okay? So, just to reinforce this equivalence, let's just play with a couple examples. So, for the next two examples, what we want to do is rewrite the logs using exponentials. Okay? I mean, practically speaking, when things are written like this, they don't seem as useful. So one of the mantras you're going to have in this section, whenever you see logs, is change to equivalent exponential form. Okay? That sort of thing should ring through your head. And so let's just practice with that very quickly. For example, if I have log of 1,000 equals 3, okay? This is a true statement, but all we're actually wanting to do here is just rewrite this in equivalent exponential form. Okay? So, what do? You don't see a number written here. We know that that's 10 to the power of 3 equals 1,000. And I don't think you'll argue with that statement. Okay, let's do another one. What if I have log of 0.001 equals negative 3? Again, we don't have a number written here. By default, it's a base of 10 to the negative third power is 0.001. And again, I think you'll grant me that that is a true statement. All right, now let's go the other way. We're going to take some exponentials and we're going to rewrite them using logs. For example, I'll write 10 to the negative second power is 0.01. Okay? Again, we know this to be the case. Remember, when you have a negative exponent, you move him down to the denominator. And so we have 1/100th, which is exactly this in decimal form. Okay? So, how would we write this in equivalent logarithmic form? Well, you write the word log. We see it's a base of 10, so we don't need to put anything here. It's not incorrect if you do. And then, remember, the way you take this is you say your exponent goes on the other side. So it's log of 0.01 is equal to -2. Okay, one more of these. And then I will make the comment that I understand that this equivalence is sometimes a bit difficult at first. I recommend you have it written down in front of you as you're doing all of these exercises, because it comes with practice. All right, what if I have 10 to the 4th equals 10,000? Again, this is certainly a true statement. We have a base of 10, so we'll just write log. And log of 10,000 equals 4. Remember, your exponent is your y value. That's the thing that's on the other side. All right. So, another comment that I want to make is as follows. And this is going to go back to the whole idea that we discussed with composition of functions and inverse functions. Okay? One quick thing I want to remind you of. So I'll say recall. When we're dealing with our inverse functions, what happens? Okay? One of the things that we saw is that our function and its inverse, they essentially undo each other. So, for example, if you start with a function, I'll call him f, and recall that we write the inverse as f inverse. Okay? What happens? Well, we take a point, x, we plug them in f, and out comes f of x. What happens when we plug this into our inverse? Remember, by definition, it takes us back to where we started. In other words, f inverse of f of x equals x. Do you guys remember that this is exactly what we did with our composition? Okay, start with a point, plug them in the first function, plug them in the outer function, and by definition, if they are inverses, you get back to where you started. Recall that we could do that with a point, we'll call them x, and we could plug them in the inverse function first. And then when we plug them into our function, again, we get back to where we started. Okay? Now, let's look at this in the context of our exponential function and their corresponding inverse function, which is a log function. So let's first start with this guy. Let's suppose my function is 10 to the power of x, and we know his inverse is log x. Okay? I'll even write log base 10 here just to reinforce this idea. Okay? So, remember, because they're inverses, they undo each other. So, for example, if I start out with some point, I'll just call him p, and I plug him in my function f, out comes 10 to the p. Okay? Now if I plug him into my function g, I think you'll grant me that we're going to go back to p, but look at what we're doing. What does it mean to plug 10 to the p into this function? It means we're taking log base 10 of 10 to the p. Okay? And because they're inverses, we've got to get back to where we started. Look at this. We start with p, we plug them into our exponential, okay, and we get that output. We take that output, plug them into the inverse, and remember, we have to get back to where we started. Do you remember that this is one of the properties? That when these two numbers match, you just get the exponent? Okay, that's where that comes from. In a similar manner, I could start with p and plug them in my function g, and then I think you'll grant me I've got log base 10 of p. Now, I can plug them into my function f, and we know that we're going to get p back. Again, what does it mean to plug this into my function f? Well, everywhere we see an x in our function f, we're going to plug in log base 10 of p. So we have 10 to the log base 10 of p, and again, that's equal to p. Okay? These are two of the properties that we discussed in the previous section of 5.0. And that's where they come from. They come precisely because these are inverse functions. Okay? And again, we can do a similar thing for e to the x and the natural log of x. Again, we know that they're inverse functions, so we know that they undo each other. So, again, I'll start with a point P, just so that we don't confuse all these x's. And we could plug them in f first, and I think you'll grant me that e to the p comes out. Now, if we take this and plug them in our function g, we know we're going to get p back. We know that it's going to be equal to p. Well, what does it mean to plug e to the p in g? Well, it means we're going to take the natural log of e to the p. And notice, again, we have this similar property. Okay? One more time. Let's go the other way. We start with p. We could plug them in g first. And so we got the natural log of p. Then we could plug them in f. Well, that means we're going to look at e to the natural log of p, and because these are inverses, we're going to get back to where we started. Okay? So, in general, let me say this. And this works for any base. In general, though, e to the natural log of p is p, the natural log of e to the p is equal to p, and similarly, 10 raised to the log of p is p, and in a similar manner, log of 10 to the p is p. Okay? These are really, really useful things. Alrighty, so now that we've established the equivalence and the fact that these guys are inverses and therefore undo each other, what I'm going to do is play around more with these properties that we played with in the last section. Okay? So, let's take some examples. Okay, so for my first group, what we're going to do is evaluate without a calculator. Okay? Again, what we're doing here is going to be looking very similar to what we did in the previous section. So, first let's start with this. Let's do log of the square root of 1,000. Okay? Now, the way I like to approach these is I see that this is a log base 10. So what I'd really like to do is get what I'm taking the log of as 10 raised to some power. And I claim we can do that. So we've got log, okay? Now, 1,000 is 10 cubed. And when you take the square root, that's the 1/2 power. Again, when you raise something to a power, raise to another power, you multiply the exponents. And now we can use the fact that they're inverses, and we could just say that this is 3/2. Okay? All right, let's take another example. What if I have, how about the log of the square root of 10? Well, now I nearly have this written as 10 to some power. I'll just write that as 10 to the 1/2 power. And so we get 1/2. Okay, what if I have this example? 10 raised to the log 1. Okay? Now, using this property, we know this is equal to 1. Another thing you could do is you could say, wait a minute, the log of 1 is 0. Okay, I'm just showing you that there's another way and it brings you to the same place. We know that the log of 1 is 0, and we also know that 10 to the 0 power is 1. Alrighty, what if I want to look at, say, the natural log of e to the 5th? Again, using the fact that these are inverses, remember you're taking 5, plugging them in your exponential, taking that and plugging it into your log. They undo each other. You simply get 5. Little anticlimactic, perhaps. What about e to the natural log of 2? Again, these guys are inverses. You simply get 2. All right, what about this one? The natural log of 1 over the square root of e. Now, we can actually do this a couple of different ways. Obviously, on any test, you're only going to have to solve it once, but I'm going to show you both ways of doing this, and again, show you that you get to the exact same place. Okay, using what we've been playing with in this particular section, what I'm going to do is write this as the natural log of e to the negative 1/2 power. Now, how did I get e to the negative 1/2 power? First off, note that this is 1 over e to the 1/2. So all I did is bring him up to my numerator, and that got rid and that made my exponent negative. Okay? Now I can use that property over there that these guys are inverses, and we're just going to get negative 1/2. Okay? Another way that you could look at this, using what we did in the last section, is you could say you've got the log of a quotient. So can't we write that as the natural log of 1 minus the natural log of e to the 1/2 power? The natural log of 1 is 0. Boy, using those properties, we could even bring that 1/2 down in front, or we could just keep consistent and say these guys cancel each other out. So we have 0 minus 1/2, which gives us that negative 1/2. So do you see how when we use these properties, you can do it one way, I can use it another way, but we get to the exact same place. It's a beautiful thing about math, one of the many. Okay, now what I would like to do is rewrite these without using logs. So express in terms of x without our natural logs. Okay, again, we're just playing with simplifying these things. Natural log of e to the 2x power. These guys are inverses. They cancel each other out. They undo each other. And therefore you get 2x. How about e to the natural log of 3x plus 2? Again, our input was 3x plus 2. We plugged it in our function. We then took the output, plugged it in our inverse, and we get back to where we started. What about the natural log of 1 over e to the 5x power? Well, first thing I would do is I would write that as the natural log of e to the negative 5x power. Again, what I did is I brought my exponential up to my numerator because my exponent was positive down here. Yes, that did give me a negative exponent. These guys are inverse functions. They undo each other, so we get back to where we started. And last but not least, for this example, what if I have the natural log of the square root of e to the x? Well, first thing I would do, as I've done prior, is I'd rewrite my square root as a 1/2 power. Okay, again, when you raise something to a power, raise to another power, you multiply your exponents, and so we're left with 1/2 x. All right, now what I'm going to do for the next few examples is as follows. This kind of shows you where we're heading with these things, okay? For example, suppose I have 1.45 to the power of x equals, say, 25. Okay? This was sort of our motivating factor, and don't worry, we're going to get a lot more in depth with solving these sorts of equations, but I'd like to get us going with a few right now. Okay? We want to solve for x. All right. Well, the problem is that x is up in our exponent, and we have no real way of getting him down. This is where the beauty of logs come in. Okay? Now, you can either use the log log, in other words, log base 10, or you can use the ln log, the natural log. You're going to want to use one or the other because that's what your calculator can compute. Honestly, I'm a natural log type of person, so that's what I usually go to, unless I have a base of 10. If I have a base of 10, I'm totally going to use log. Okay? So, in this case, notice I don't have a base of 10, so what I'm going to do is use either one. I'm just going to take the natural log of both sides. Now, remember, equations are like kids. Whatever you do to one, you got to do to the other. So in other words, if I'm going to take the log of one side, in order to keep equality, I need to take the log of the other side. Now, you might ask, why did you do that? It looks a heck of a lot more complicated. Well, now we're going to go back to one of those properties of logarithms that I had mentioned to you was one of the most often used. Okay, remember, when you have the log of something raised to a power, you can bring your exponent down in front. So all I did from here to here is use my property of logarithms that say that I can bring my exponent down in front. Now, the natural log of 1.45 is just some number. The natural log of 25 is just another number. Okay, we want to know what x is. We want to get them alone. Well, how do you undo multiplication? You divide both sides. So what I'm going to do is divide both sides by the natural log of 1.45. On my left side, they're going to cancel. That was the whole point. And on my right side, I get the natural log of 25 divided by the natural log of 1.45. And if you're at all curious, you can solve this on your calculator. And going to 2 decimal places, we're going to get about 8.66. Okay? And you know, you can at least check your answer somewhat. I just plugged in 1.45 to the 8.66 power, and when I did, I got 24.97. Okay, so within round off error, we did a pretty good job here. All right, now let's take this example. E to the 0.12x equals 100. In this case, I wouldn't even think to use my log log. Okay? Why? Notice the base here, you certainly can, mind you, but notice the base here is e. Okay? So, whenever you have a base of e, you want to use your natural log. Just like whenever you have a base of 10, you want to use your log log. Okay? Let me show you why. If I take the natural log of both sides, again, we want to get this value of x, and we really don't have a way to get to our exponent. We have the natural log of e to the 0.012x, excuse me, I put my decimal point in the wrong place there, equals the natural log of 100. Again, whatever you do to one side of an equation, you do to the other side. Now, because these are inverse functions, they undo each other. Notice my left-hand side just becomes 0.12x, and that's equal to the natural log of 100. We can certainly get x alone by dividing both sides by 0.12. So I claim that x is equal to the natural log of 100 divided by 0.12. Now, I'm going to compute that, and to 2 decimal places we get 38.38. Okay? I want to show you something. This is not something that I would do in practice, but I want to show you that you would get to the same place if you chose to use log base 10. If I took the log log of both sides, well, this is kind of cute to do anyway, right? Because check this out. What would we do here? We would bring our exponent down in front. We would have 0.12x times the log of e. We could leave this as log of 100, but you guys, I can't resist. Isn't 110 squared? These guys are inverse functions, so we just get 2. All right, we want to get x alone. What's the problem with this left side? Well, not only are we multiplying by 0.12, but we're also multiplying by the log of e. So in order to get x by his lonesome, I need to divide both sides by that mess. So I claim x is 2 divided by 1.2 log e. And if you plug that into your calculator, you will see that you're going to get the exact same thing. Isn't that so cute? I just love that. Alrighty, so let us do one more example for now. Let's suppose we have 48 is equal to 17 times 2.3 to the w power. Alrighty. Well, what do we want to do here? Again, we want to find the value of w, okay? And yes, we do want to take the log of both sides. We could do the log log or the natural log. One is not easier than the other in this situation. But the problem is we don't have our exponential isolated, okay? So before you take the log of both sides, what you want to do is isolate your exponential, okay? We're going to be solving certain equations like this where we actually have an exponential on both sides. But one of the things you're going to see is we're going to want to put our exponentials on one side and our numbers on the other. Okay? So the first thing that I'm going to do is divide both sides by 17. So I have 48 over 17 is 2.3 to the power of w. Now, we could leave it as 48 divided by 17, or you can get a decimal approximation. Either way. What I'm going to do now is take the log of both sides. Again, log log or natural log, you will get the same thing. So I have the natural log of 48 over 17 is the natural log of 2.3 to the power of w. My next step is to bring my exponent down in front. So on my left, I have the natural log of 48 over 17, and on my right, I have w times the natural log of 2.3. In order to get w alone, I'm going to divide both sides by the natural log of 2.3. So I have the natural log of 48 over 17 divided by the natural log of 2.3 is equal to W. It doesn't look pretty, but our calculators can certainly compute this without a problem. And what we're going to get is as follows, approximately 1.25. Don't worry, we will be playing more with these very soon, but I think that that's enough for this section. Thank you.